So good evening, and thank you for the invitation to come to talk to Liverpool AS once again. So this is a physicist's view of how the universe came to be and how we ended up with the observable universe that we see today. So to remind you what it is we're trying to explain, this is, it looks like a bit of CGI, a bit of animation, but this is perhaps better thought of as a 3D atlas. So although there is a certain amount of license in animating these galaxies have been plotted according to their known position in the sky and their known distance from Earth. In other words, we've mapped out the 3D positions of quite a large number of galaxies. And in this particular case, we're doing a sort of virtual fly-through of this 3D atlas. So the thing we notice is the universe isn't empty. It's full of stuff. Apparently, there's lots of galaxies out there. And we also notice that the galaxies are not uniformly spread. They are definitely bunched together. Every once in a while we see filaments, we see long stretches of what looks like lines of galaxies. And occasionally we come across a patch which seems to be rather sparsely populated with galaxies. So if this is what our observable universe looks like, then the question is, can we basically explain how it came to end up looking like this? In other words, we're not going to go through the entire 13.8 billion year evolution of the universe, but we're going to ask, where did all this stuff come from? When we look out into the universe, not just the few million galaxies that we see here, when we look out into the universe and go as deep as we can with something like the Hubble Ultra Deep Field, we come to the conclusion that there are trillions of galaxies in the observable universe. And each of those galaxies probably has got maybe hundreds of billions of stars. So there's an awful lot of stuff out there, and the question is, where did it all come from? So we know it's out there. What are its origins? So I'm talking about the creation of the universe. When did it happen? As best guess, and it's always a guess, it's always based on our understanding of what we see, it looks like the universe is 13.8 billion years old. That's when it all started. How long did it take to make the universe? It took about 3 minutes to make our universe. When did it happen? Sorry, where did it happen? Well, it happened everywhere. It didn't happen at a point in space because basically space didn't exist until the Big Bang created space and created time. Why did it evolve the way it did between that point 13.8 billion years ago and today? Well, it evolved the way it did because of the laws of physics. And how do we know all of this? How do we know it's 13.8 billion years old? How do we know what happened 13.8 billion years ago? Same answer, the laws of physics. So we come to the question, well, how do we know what happened 13.8 billion years ago? Are we sure the laws of physics then are the same as the laws of physics as we understand them today? In other words, if we were looking at the universe as a chess game, we can ask, looking at that chess game, can we figure out what the rules of chess are by looking at that picture? It's the same sort of problem that we have in cosmology. We can't sit and watch the universe evolve. We effectively have got a snapshot of the universe as it is now. By looking at the universe, can we tell what the rules of the game are? In other words, the rules that dictated how the universe came to be and how we end up with the observable universe that we see today. So we can ask the same question. If we were to look at a game of chess, can we tell what the rules of chess are by looking at that picture? And the answer basically is no, we don't have enough information. It looks like there's two slightly different shiny colors, so perhaps this is a game between two people. There are different shapes sitting on different squares, and one of the pieces seems to have fallen over. Is that significant? Well, we don't know unless we know what the rules of chess are. And it's the same sort of problem if we look at a galaxy. How can we tell the rules of the game? How can we tell what the rules are that made that galaxy come to be? Just staring at that picture doesn't help us. We can't sit and watch that galaxy evolve because it moves too slowly. It might take hundreds of millions of years to do one rotation, and we haven't got the patience to sit and watch it. It would help if we had a video of somebody playing chess. If we were to watch a video of two people playing chess, then we could probably figure out what the rules of the game are by watching how they move. But we don't have that option in the sense of we don't have the option of just videoing the universe for a couple of billion years and then seeing how it changes. So it's the same sort of problem. With galaxies, we have a way around the problem. Instead of taking one picture of one chessboard, what if we were to photograph 1 billion people playing chess? In other words, it's still a snapshot rather than a video, but maybe we get an idea. If we look at 1 billion different chessboards, maybe we can figure out what the rules of the game are. And that's what we do with galaxies. Instead of looking at one galaxy, we look at as many galaxies as our telescopes will allow us to point at. And of course, a snapshot of the universe until recently, the Hubble Ultra Deep Field was one of the deepest. Now we've also got the Webb Deep Fields to add to that. It won't be long before the Webb actually looks as deep as look in the same region as the Hubble Ultra Deep Field. The Webb intends to revisit the same patch of sky, and we should be able to go a lot deeper. But that's how we get around the problem. If we can't watch things changing in real time, what we can do is take snapshots. And if we take snapshots, we get an idea of what lots of individual galaxies are doing. And because of the finite speed of light, some of these galaxies are fairly close and fairly young. Some of these galaxies are very distant, and we're seeing them as they were many billions of years ago. So it's not quite as good as a video, but we do have that time element as well. But surely the universe is a very complex thing. How can we possibly ever hope? How can we be so arrogant as to believe we can possibly work out what the rules of the game are for the entire universe? Just looking at a tiny snapshot of our local neighborhood, perhaps some of you recognize this particular part of Orion, the Great Nebula off to the right, the Horsehead Nebula down in the bottom left there. So this is just a little bit of our local neighborhood, and it looks horrendously complicated. Surely the rules of the game that dictate that this should come into being must be extremely complex. Well, one thing we have to do is to separate complex from incomprehensible. Because if you look at this particular collection of colored dots, it's a mathematically generated set of pixels. Some of you may recognize it as a very small part of the so-called Mandelbrot set. So a mathematical formula generated all of these pixels, and if we zoom in, we see enormous amounts of detail. And if we wish, we could zoom in by a factor of 10, or a factor of 1,000,000, or a factor of 1,000,000,000, or a factor of 1,000,000,000,000, and we would still see detail. In other words, this mathematical construct, this mathematical set of colored pixels is based on a mathematical formula, but it's not just the 1,000,000 or so pixels that you can see in this particular image. It is trillions upon trillions upon trillions of pixels. Arguably, it's an infinite number of pixels generated by a mathematical formula. So if that is apparently a very complex structure, some of it looks like it has certain motifs. This sort of blob here looks like it's the same blob there, but a bit smaller and a bit smaller and a bit smaller. And it bears a passing resemblance to this one. But if we look in detail, they're not the same. None of this ever repeats. It's a bit like saying we look out into the Milky Way, we see lots of stars which might look similar to each other, but none of those stars are actually the same. This pattern of pixels is the same. It might look like there's some similarities when we look at different regions, but in fact, none of the patterns of pixels ever repeat, even if we zoom in billions or trillions of times. So the question I phrase is, well, what is the rule of the game here? This is an incredibly complex pattern. You could argue this is infinitely complex. So how complex is the mathematical formula that generated each and every one of the infinite number of pixels in the image? And the answer is there. That's the mathematical formula that generated. We don't have to worry about what Z and C represent. They're just numbers. But basically, that formula generates the entire Mandelbrot set. So just because something looks incredibly complex does not mean the rules that generated it, the rules of the game, the laws of physics, if you like, are necessarily very complex themselves. I like this particular quote from Einstein, who summed it up very nicely. The most incomprehensible thing about the world, and as far as I can see, the world means the entire observable universe. The most incomprehensible thing about the universe is that it is comprehensible. There is no particular reason why the universe owes us anything. The fact that we can make inroads to understand how the universe works is fairly incredible in itself. and it's not altogether obvious why we are able to understand the universe, but apparently we can, despite it being incredibly complex, and complex does not mean incomprehensible. Even though it's very complex, we can still, with a little bit of thought, start to understand a lot about the universe. So let me describe the flow of thought that helps us get a handle on the universe as a whole. We've known for 100 years or so, by simple observations, well, not necessarily simple, but by observations through telescopes of galaxies and the light from these galaxies, we know that distant objects are moving away from each other. We come to the conclusion that the universe is expanding. We've known this for about 100 years or so. We also have other observations. For instance, we have observations of how does physics actually work on Earth. Forget galaxies and stars. If we were to do experiments on Earth, can we figure out what stuff is made of? Can we figure out that the world is made of molecules, and molecules are made of atoms, and atoms are made of smaller stuff, etc.? Yes, we can do various experiments on the nature of matter, what holds matter together, what is light, how does light interact with matter, etc. We can do various experiments, including smashing stuff together in the Large Hadron Collider, for instance, the LHC. And that gives us a handle on how we think the world is put together. And if we assume the world is put together in the same way that the moon is put together, and the way the sun is put together, and the way the solar system and the Milky Way is put together, then we can use what we learn on Earth to extrapolate to the rest of the universe. But we do have to make two very important assumptions. If we want to understand the universe in which we live, we have to make two assumptions which we cannot prove. And the assumptions are that the laws of physics in one place are the same as the laws of physics in another place. And also that the laws of physics do not change with time. The laws of physics now are the same as the laws of physics in the past and are going to be the same as the laws of physics in the future. If we throw away either of those two assumptions, we cannot make any progress whatsoever. If I try and understand some aspect of either gravity or some aspect of why does this particular object in my hand produce a red laser beam, if it was a question of, well, I can build one of these here according to the laws of quantum mechanics, according to the laws of solid-state physics, but in France it wouldn't work because the laws are different over there, then we wouldn't make any progress. If the laws of physics were different in Australia and in the UK, we would never be able to come to any conclusions at all. And if the laws of physics I deduce by looking at the nature of light or the nature of matter or observing different parts of the universe, if the laws change tomorrow, again, I cannot make any progress. Understanding the laws now is useless if they're going to change tomorrow and the day after and the day after. So the only way we can make any progress at all is to assume that the laws of physics are immutable, that they are what they are, they always have been and always will be, and they are the same everywhere. Part of the cosmological principle. The Earth isn't anywhere special. The solar system isn't anywhere special. The Milky Way isn't anywhere special. We are not in a privileged part of the universe, so whatever we find on our particular planet orbiting our sun in our galaxy, it would be the same if we picked any other planet in any other solar system in any other galaxy. The laws of physics are the same everywhere. If we assume that that is the case, and from now on we're simply going to assume that the laws of physics are immutable, then we come to the conclusion, based on our observations, that the universe must have been created in a very hot, dense state some 13.8 billion years ago, and has been expanding and cooling ever since. And that's the state we find ourselves in now. But the really big question, the one I'm going to try and answer this evening, is when we look into the observable universe, and occasionally I'm going to talk about the universe, what I mean is the observable universe. By definition, we can't observe anything else but the observable universe. But rather than continuously saying observable, I'm just going to use the universe as a shorthand for everything we can see in the observable universe. So when we look at everything that we can see, all of these trillion galaxies containing hundreds of billions of stars and all manner of gases and dust and all the other material, where did all that stuff that we see today, where did it all come from? And one question we have to ask is, Well, if we think the universe started 13.8 billion years ago, how far back in time can we go before we are not absolutely sure whether the laws of physics as we understand them today necessarily apply? So in other words, if we go back in time, if we go to the first year, I know year and month, etc., are rather modern day understandings, but we know what we mean by a year and a month. If we go back to the first year of the universe, 13.79999 billion years ago, do we think the laws of physics as we understand them today still applied when we go back in time to just the first year after the Big Bang? Absolutely yes. What about the first day? Yes. What about the first hour? Yes. What about the first minute? Yes. What about the first second? Yes. What about the first millisecond after the Big Bang? Do we think the laws of physics at that point are still the same as the laws of physics as we understand them today? Yes. What about the first microsecond? Yes. What about the first nanosecond? Yes. What about the first picosecond? Maybe, maybe not. A picosecond is as far back in time as we can go before we have to admit we're not actually sure what happened before this point in time. So it's a ridiculously short length of time after the Big Bang. A picosecond is 1/trillionth of a second, 1/millionth of 1/millionth of 1 second. But that's about as far back as we can go in time before we say we cannot, with hand on heart, say that we really understand what was going on at that point. Before the first picosecond, we are on, as far as a physicist is concerned, shaky ground. But everything after that, after the first picosecond, after the first 1/trillionth of a second, everything from that point up to the current present day is reasonably well understood. And we believe the laws of physics have not changed from a picosecond to the present day. I'll explain why it is that that picosecond is the sort of watershed between the two regions where we do understand or don't understand. So what I've said so far has been a very long-winded introduction to what I'm saying this evening. I've just given you a 15-minute introduction. I'm going to show one slide, which is just a basic idea to make sure everybody's on the same page before we launch into what happened during the Big Bang and the first 3 minutes after the Big Bang. So I'll be talking about the first fraction of a second, and then the first few seconds, and then the first few minutes. I can't keep pace with that all the way up to the present day. Obviously that will take a while. So I'm going to change gear at that point and fast forward 377,000 years. Again, there's a good reason for that number. It's not just picked out at random. And then in a few seconds, I will summarize the next 13.8 billion years, because again, we don't have time to talk about all aspects of stellar evolution and galactic evolution, because we're talking mainly about where did the stuff come from. I mean, when it comes to stars, I gave you a talk quite a few years ago about stellar evolution, and in that particular talk I said, as long as you've got plenty of hydrogen, you can make all the stars and galaxies you like. But the question is, the elephant in the room at the time was, where did all the hydrogen come from to make all those stars and galaxies? That's precisely the question we're addressing today. So we've done the introduction. I'm going to deal with a few basic ideas and then go through this particular timeline. So a few basic ideas. Some of this will not be in any way a surprise to you. We're going to start with the statement that we are made of atoms. No intake of breath at that point, so I think you're all happy with the fact that we are made of atoms. Great. Atoms are made of certain particles. We have a nucleus, which is made up of positively charged particles, and we have a little buzzing set of electrons going around them, negatively charged particles buzzing around them. So an atom, if we wish, can be separated into a positively charged nucleus and negatively charged electrons. As far as we can tell, electrons are fundamental. Fundamental to a physicist means there's nothing inside them. They're not made up of anything else. You can't take an electron, cut it in half, and look inside and say, what is an electron made of? As far as we know, they just are. They are particles, fundamental particles. They're not made of anything else. Whereas a nucleus is different. A nucleus is made of other stuff. We can take a nucleus, cut it in half, and have a look inside. And we find that a nucleus is actually made up of two types of particles, which we call protons and neutrons. We're not going to worry too much about the particle zoo and how particle physicists go about naming all the particles. We're just going to treat these as labels in what is going to come in terms of building up the universe from the bottom up. Now, protons and neutrons themselves are not fundamental in the sense that you can take a proton and at least in principle you can cut it in half and have a look inside. The same is true of neutrons, but I'm just following the family tree of protons here. A proton is made of other stuff. At the moment, the other stuff, to the best of our knowledge, are particles that we call quarks. Don't worry about the stupid name that they were given. They're just particles which, again, like electrons, do not appear to be made of anything else. At the present day, we do not think that you can take a quark, cut it in half, have a look inside, and see what they're made of. So we believe that electrons are fundamental particles and quarks are fundamental particles, and you can build anything you like with this Russian doll idea of if you put quarks together, you make protons and neutrons. If you put them together, you make a nucleus. If you add a nucleus to some electrons, you make an atom. If you add atoms together, you make molecules. If you put molecules together, you make cats and dogs and us and trees and pretty much everything else. So that is how the universe is put together. But what we notice is that it takes a certain amount of energy to take an atom and rip it apart and separate an atom into its constituent parts of a nucleus and electrons. It takes more energy to take a nucleus and separate it out into its protons and neutrons. It takes even more energy to take a proton and separate it into quarks, if we could ever get round to doing that. Turns out there's a problem doing that, but we don't need to worry about it. The point is, there's an implicit energy scale from low energy to high energy. Molecules are low energy, and if we want to break them down into atoms and break the atoms down into smaller and smaller constituents, like a sort of Russian doll, open it up, see what's inside, open it up, see what's inside, open it up, see what's inside. Every time we open another Russian doll, it takes more and more energy. To a physicist, low energy is cold and high energy is hot. If particles have a lot of energy, then we talk about that being high temperature. And remember, on the previous slide, we said, well, we believe, because of the expansion of the universe, because of observation, it looks like the universe is expanding and cooling, and a long time ago, it was a lot hotter. In the early days of the Big Bang, it was very hot, and ever since then, it's been expanding and cooling. So if that's low energy and that's high energy, that's cold and that's hot, the universe started hot and is cooling down. So time is running upwards in this particular diagram. In other words, the universe started down here and is cooling off. And as it cools off, it is possible for protons to get to be made out of quarks, and then as it cools further, protons and neutrons can get together to make a nucleus. But we can't simply make everything. Even if we had all the constituents, even if we had a shed load of quarks, we can't suddenly make atoms. We have to wait until the universe is cold enough to make atoms. Because if we try and put all of these things together when the universe is still hot, they will just immediately fall apart again. In other words, there's a certain temperature at which quarks can make protons. There's a certain temperature at which protons can make a nucleus. There's a certain temperature at which nuclei can get together with electrons to make atoms. And that is a time sequence. So the universe is quite definitely built from the bottom up, according to our current understanding. And we'll have a look at this process in more detail. But again, the elephant in the room is what happened at time t equals 0? What happened at the instant of the Big Bang? But I've already said we don't really understand anything before the first picosecond. So anything before the first picosecond includes time equals 0. So no, we cannot definitively say what happened at the instant of t equals 0. It is beyond, at the moment, our ability to probe in any sort of physics experiment. There is nothing we can do that gives us a definitive answer. You can come up with as many hypotheses as you like, but at the moment we don't have evidence that proves one hypothesis versus another. A lot of people seem to think, well, quantum mechanics is fairly weird. Maybe it was a quantum fluctuation, a fluctuation in which energy is borrowed from nothing. And that sounds weird, but yeah, it is weird, but then quantum mechanics is weird. Separate talk, by the way. So quantum mechanics is weird, and quantum mechanics allows you to borrow something from nothing. It is perfectly okay to borrow something from nothing. It's like having an infinite-sized bank from which you can borrow money, but you must pay back the loan quickly before the universe notices that you've taken the money out. So just like with taking money from a bank, in this particular case we're talking, if you like, energy, but it doesn't really matter if we're talking energy or matter, because we know energy and matter are, as it were, interchangeable according to E equals mc squared. So just like you can borrow money from a bank, and the more you borrow, the faster you have to pay it back to avoid paying huge interest, it's the same with energy being borrowed over a given time from the bank of nothing, if you like. How big can this fluctuation be? Even though we're starting with nothing, how much can we suddenly bring into existence? Well, the amount of energy we borrow multiplied by the time we have to pay it back, there is an upper limit according to the rules of quantum mechanics, according to the laws of physics that we currently label quantum theory or quantum mechanics. You can either borrow a lot of energy for a very short time, or you can borrow a tiny bit of energy and you've got ages to pay it back because the universe isn't going to notice for quite a while. The total energy in the universe, it's thought, could actually be zero. When you look at all of the matter in the universe and all of the gravity in the universe, all of the matter gives you a positive contribution to the energy, all of the gravity gives you a negative contribution to the energy. When you add it all up, we're not absolutely sure, but it looks like the answer might be the total energy budget of the universe might be zero. And if you've got energy times time has an upper limit, but the amount of energy you're actually borrowing is zero because of the balance between matter and gravity, well, maybe the universe is going to allow us an infinite amount of time before we pay back the loan. This always sounds like a complete con, but then quantum mechanics is really weird, and as far as we can tell, quantum mechanics does allow us to make particles out of nothing. We don't need to have something there in the first place for an electron to pop into existence. That is okay according to quantum theory. So maybe quantum theory allows us to borrow the energy we need to make all of the matter and all of the associated gravity back 13.8 billion years ago. But we do not know. It is only a hypothesis because we cannot test that hypothesis in any meaningful way. But if we go forward in time, and by forward in time, I'm talking about a time, let me just take my little prop here. We're talking about that point after the Big Bang. At a time of 10 to the minus 35 seconds after the Big Bang, the observable universe is now about that big. So remember, the observable universe is currently about 100 billion light years in diameter. It's actually about 46 billion light years in radius. So roughly speaking, 100 billion light years across is our current observable universe. But if we run the clock back and say, well, the universe is expanding, but if we run the clock back, that 100 billion light years must have existed in a smaller volume at this particular time, 10 to the minus 35 seconds, then the observable universe would have fitted into something basically a few centimeters across. We're not, remember, sure what's going on outside the observable universe, but we can say that that particular volume used to be a lot smaller. So it's difficult to get your head around that everything that we currently see in the universe used to be a lot closer together. But that's the conclusion we come to when we say the universe is expanding, so everything must have been closer together in the past. Just like a golf ball, I like this analogy because the universe is not smooth, it has dimples in it. Just like a golf ball has got dimples, so the early universe has got dimples. The early universe was not perfectly smooth collection of whatever particles existed at the time. Dimples in this context doesn't mean dimples on the surface. Dimples means variations, small variations in density and temperature across the universe. When the universe expanded, these dimples, when the universe was much, 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 much bigger than the size of a golf ball, these variations in density ultimately gave rise to clumps of density which gave rise to galaxies and superclusters of galaxies that we see today. In other words, all of the large-scale structures that we see are based on these dimples in the golf ball. That's why we think those dimples exist, because if those dimples didn't exist, we can't explain where all the galaxies have come from. We are still, remember, in this no man's land of making assumptions. This is just a hypothesis. We don't know that this is the case. At the moment, this is just a hypothesis. But then we fast forward to a picosecond. Remember, this is the watershed where I said, I think everything from a picosecond onwards, we're on fairly solid ground. So this is an important watershed point. 1 picosecond after the creation of the universe, it's expanded from a golf ball to about the size of a solar system. Yes, the solar system doesn't exist yet, but just to give you an idea of scale, it is light hours across, and it's taken a picosecond to go from essentially nothing to a few light hours in diameter. So the universe has expanded very, very, very fast. And the temperature has fallen now to a rather balmy 10 to the power 15 Kelvin. So a mere, what's that, a mere 1,000 million Kelvin. Substantially hotter than the core of any star that we can ever think of. And we believe that the universe is made of lots of fundamental particles. It's sometimes called a quark soup because there are lots of quarks in there, but you shouldn't take that as meaning that there are only quarks in there. There's a whole load of fundamental particles like quarks, electrons, and probably other particles as well. But the point is that at this particular point in time, the temperature of the universe, although it seems ludicrously high, if you think of how energetic the individual particles would be at this early stage of the universe, that's the same amount of energy that we can reproduce in the Large Hadron Collider. In other words, we can generate particles with the same energy as the universe had 1 picosecond after it's born. And hence we can do experiments. We can say, if this particle has got this much energy, how does it behave? We can actually test it. We can actually observe things in a particle accelerator and start asking questions. If the universe had that much energy at that time, how did all this stuff behave? So it's no longer conjecture. We can test our ideas in an accelerator on Earth now. Well, we've had an accelerator for quite a few years now, and we are currently testing various ideas. And so, from this point onwards, the universe is going to get colder. It is going to get easier and easier to reproduce the amount of energies that the universe had. And therefore, from 1 picosecond onwards, the universe is cold enough for us to actually test things in the laboratory. And hence, we believe that the physics that we see in the early universe from this point onwards is indeed what we observe when we do experiments in the laboratory. So that's why it's not just a statement of arrogance. That's why we believe that the physics from this point onwards is something that we can get a real solid handle on. I'm aware of the time, so in just a few minutes I'll stop for the first tea break. But just to get over the next hurdle, as it were, if we borrow energy, we can make matter. If we borrow matter, we can make energy. Energy and matter are continually exchanging backwards and forwards because E equals mc squared. If we've got one, we can make the other. Originally, matter and antimatter are made in equal amounts. Antimatter is just the opposite of matter. For every particle that exists, it has an anti-equivalent. An electron has an anti-electron partner, if you like. It looks, to all intents and purposes, like an electron, but it has the opposite electrical charge. Same mass, same behavior, except the opposite electric charge. And that's what we mean by antimatter. Every particle of matter has an equivalent opposite particle of antimatter. And originally, they are made in equal amounts. In other words, energy, I don't know how to represent energy symbolically other than with a big E on the screen. So energy can be used to make matter and antimatter. Now, it's probably not going to be a tangerine and an anti-tangerine. It's probably going to be a quark and an anti-quark, or an electron and an anti-electron, or a neutrino and an anti-neutrino, or a particle and an antiparticle. The point being, it doesn't matter. Energy can make matter and antimatter, and those particles of matter and antimatter very quickly are going to annihilate and produce energy. because E equals mc squared, forwards and backwards. Energy can make matter and antimatter, which can then annihilate and make energy. And that energy can make more matter and antimatter. Not necessarily the same particles again, it could make something completely different. Probably not hot dogs, and probably not anti-hot dogs, but it doesn't matter. It can make something and it's anti-equivalent. It can make quarks and anti-quarks, and then it can make electrons and anti-electrons. Then it can make something and anti-something. And it will be going backwards and forwards, matter and antimatter making energy, back and forth, back and forth. But somehow, through a process that we do not yet fully understand, somehow matter gained a very small excess over antimatter, and it was just a small excess. And I'll finish after this slide so that we can have a cup of tea. If we imagine that's all the matter that's made from our energy making matter and antimatter, somewhere along the line, a smaller amount of antimatter was made. I've indicated here it's sort of 1 part in 10 is the difference between how much matter was made and how much antimatter. It wasn't 1 part in 10, the difference. The discrepancy was 1 part in a billion, a tiny, tiny, tiny discrepancy between the two. But what that means is that matter and antimatter can annihilate and make energy, and so you get energy, usually in the form of light. So in other words, each of these particles of matter and antimatter are going to annihilate and make a photon of light, maybe a high energy photon of light, maybe a gamma ray, but it doesn't really matter, it's just radiation. But there's some matter left over, which hasn't got an equivalent amount of antimatter to annihilate with. Remember, this is just 1 part in a billion that's left over at the end. So what are we expecting to see? We're expecting to see a universe which is actually full of huge amounts of radiation and a tiny amount of matter, because it's just that 1 part in a billion which is left over at the end there. And that is indeed the universe that we see. If we look out into the universe, we find billions of photons of radiation for every particle that exists. Even though the number of particles out there is huge, in all of the stars, in all of the galaxies, the amount of radiation, the number of photons of light, outnumber the particles of matter by a factor of about 1 billion to 1. So that is the light that we see in the universe, and the bit on the end there is you, and me, and cats and dogs, and trees and mountains, and the Earth, and the Sun, and the Milky Way, and every other galaxy in the observable universe is that little bit that's left over that didn't have any antimatter to annihilate with. So on that rather interesting thought, I think perhaps, given I've had half an hour, this is the point to have a quick tea break, and we'll be back again shortly. Okay, we're back from the tea break. And where we left it was to say that 13.8 billion years ago, a whole load of matter and energy came into existence, perhaps borrowing something from nothing. And the energy made lots of matter and antimatter, but somehow, at the point perhaps about a picosecond or so after the Big Bang, there became an imbalance of the matter being made and the antimatter being made. We don't fully understand what happened and what caused that imbalance. Why didn't the universe just make equal amounts of matter and antimatter? Because that's what normally happens. But as a consequence of that, the matter and antimatter annihilated, producing 1 billion photons of light for every particle in the universe. And that little tangerine on the end there represents all the matter in the observable universe. There doesn't appear to be any antimatter left, apart from tiny, tiny, tiny amounts. So most of the observable universe appears to be essentially 100% matter. And it's just as well there was an imbalance, because that is us on the end there. So we have an imbalance, meaning we have matter and we have a universe full of photons of light. We're now going to go forward from a picosecond to a mere millisecond into the birth of the universe. Matter and antimatter are continuing to pop into and out of existence. This whole process of energy makes matter and antimatter, matter and antimatter annihilate to make energy. This process is going backwards and forwards essentially continuously. When we get to the point of 1 millisecond, it is possible to make protons and neutrons. Now, we don't have to worry about the detail, but a proton is basically just a bag of 3 quarks. If 3 quarks get together, 3 quarks with particular properties, we call that collection of quarks a proton. That's just the name we give to a collection of quarks. And similarly, a different collection of quarks we call a neutron. So we're not going to worry about the particle physics. We're not going to worry about exactly why different quarks have different properties. But a group of quarks with a particular set of properties are what we call a proton, and a slightly different arrangement of quarks is what we call a neutron. And they can be continually turning into each other backwards and forwards. In other words, protons can turn into neutrons, neutrons can turn into protons. They are very similar in energy. Those of you who remember your physics will remember that actually there's a different charge on these. Protons are positively charged, neutrons are neutrally charged. So yes, there are some electrons floating around as well. Let's not worry about the fact that there are other electrical charges in the system. All we're worried about here is the fact that quarks can get together in particular ways that we label as this is a proton or this is a neutron. When we move forward to 1 second, we look at how many neutrons and protons we have. 1 second after the Big Bang, the universe, remember the universe is still expanding and cooling all the time, so after 1 second the universe has cooled to about 1 billion Kelvin. That might sound really hot, but remember the cores of some stars might be hundreds of millions of Kelvin, so it's not a ridiculous number compared to the sort of temperatures that are still around today in certain locations in the observable universe. But now the universe has cooled down after 1 second, now that it's only 1 billion Kelvin, it is not really hot enough for protons and neutrons to readily swap backwards and forwards. Remember the Russian doll model. As the universe continues to cool, it is possible for structures to be made. Small structures will get together to make larger structures, etc. Protons, then a nucleus, then atoms, then molecules, etc. So at this particular point, it's really too cold for protons and neutrons to change much. We know that protons are a little bit lighter than neutrons. How do we know? Because we can measure it in the lab. We can measure the mass of a proton and the mass of a neutron, and we find they're slightly different. And we have no reason to believe that protons 1 second after the Big Bang are intrinsically any different from protons that we can measure in the laboratory. Just because 13.8 billion years have passed does not mean that a proton is any different. The laws of physics are the same, so a proton is a proton is a proton is a proton. Always was and always will be. So we believe that those protons were definitely lighter than neutrons because they are today. And if they're different, it's only a small difference, they're lighter by about 0.1%. So protons outnumber neutrons. Even though it's only a tiny difference, the universe makes more protons than it does neutrons. This is crucial to what's going to come next in terms of understanding why the universe is the way it is. Why does the universe make more protons just because they're a little bit lighter? Well, it's because nature always favors the lower energy. Nature always favors the easy route. If there's 2 ways of doing things, nature will always take the easy option. If these particles represented in red, which are the protons, are lighter than these particles represented in blue, which are the neutrons, the universe will make more of them because they're lighter. They're easier to make. E equals mc squared. If they're lighter, it takes less energy to make them. So the universe ends up making a particular ratio of protons to neutrons, and the ratio happens to be 3/4 to 1/4. Why do we know that ratio? Because we work out what the temperature was at a particular point in time, and we can calculate at that point neutrons and protons can't change, and at that point we can calculate using the laws of physics that we understand today by measuring in the laboratory, we can calculate that the universe 1 second after it was born should have made this many protons and this many neutrons. I'm just representing them by taking a set of, 16 objects here and showing the ratio of the red to the blue, the protons to the neutrons. So nature always favors the lower energy, and hence nature always favors the lower mass. Protons are lighter than neutrons, therefore the universe makes more of them. Now we're going forward from seconds to minutes. Now, we know that neutrons are unstable. How do we know that neutrons are unstable? Because we can measure them in a laboratory. And a neutron today is unstable. If you take a neutron and leave it on its own, in 15 minutes, it will decay into other particles. A neutron today is no different from a neutron 13.8 billion years ago, so the neutrons back then will decay as well. Some of them will decay into protons. So the ratio of red to blue has changed. Two of the blues have now changed into reds because after about 100 seconds or so, some of those neutrons will have changed into protons. So the ratio is now the ratio of 7:1 or 14:2, taking the 16 objects that I'm showing there. After 100 seconds or so, the universe is now relatively cool, only 100 million Kelvin. And this is the point at which the nuclei of atoms can start to form. Up till now, we've just had protons and neutrons. But now, it's cold enough, Russian doll again, we've waited long enough that the universe is cold enough that protons and neutrons can start attracting each other. They can get together. There are nuclear forces that can attract protons to neutrons. Up to this point, the universe was too hot. Up to this point, if you try and get a proton and a neutron together, they're just too energetic. The universe is too hot, the particles are too energetic, they'll just fly apart. But now the universe has cooled to the point where it is possible for protons and neutrons to get together. And what they really want to do is two protons want to get together with two neutrons. So this little golf ball model I've got here is one of the most stable structures in the universe. If you've got two protons and two neutrons, they want to stick together like this because it's a very stable structure. And so if you've got a whole load of protons and neutrons, two of them will get together with the neutrons. But of course, you're left with lots of bachelors. Two of the protons will get together with the two neutrons, but you're left then with 12 bachelors who haven't got any neutrons to pair up with. Even though they would dearly like to, they're left as individual protons. This structure of two neutrons and two protons is what we today call helium, or at least the nucleus of a helium atom. Sometimes we call them alpha particles, but they're the same thing. The structure, which is two protons and two neutrons, is the nucleus of what we will eventually call a helium atom. And of course, that means the universe is full of helium, but also this much hydrogen. So we can predict that after 2 or 3 minutes or so, given that after this point you can't change things, at this point, after 3 minutes or so, the relative abundance of hydrogen and helium is fixed. You now can't change it. Okay, eventually you might be able to make stars and start doing some transformations, but as far as this birth of the universe is concerned, at this point in 3 minutes, we've made this much hydrogen and this much helium. So the question is that prediction right? This is the prediction of the Big Bang Theory that says if the Big Bang Theory is correct, you would expect the universe to be, by mass, 3/4 hydrogen and 1/4 helium. If we look out into the universe and we look at what's out there, stars don't actually occupy that much of the mass of the universe. In fact, it's a bit surprising, but most of the mass that's out there is actually gas. So yes, some stars have taken hydrogen and have started to convert it into yet more helium, but if you work out the totals of what's out there, it's dominated by the amount of gas that was made in the first 3 minutes. And when we look at the relative abundance of how much hydrogen is out there and how much helium is out there, it is this ratio, 3/4 hydrogen to 1/4 helium, measured by mass. Rather than just the number of hydrogen atoms, if we just work out the total mass of hydrogen and the total mass of helium, 3 parts hydrogen for every 1 part helium. That's what the Big Bang Theory predicts, and that's what we actually see. We think that's what was made in 3 minutes, and it hasn't significantly changed in 13.8 billion years, even though stars are doing their best to convert whatever hydrogen they can into yet more helium. So this is one of the many reasons why we think the Big Bang theory is correct. It makes a prediction that we can actually go out and measure. We can test. We can measure how much gas there is in the universe, what's the abundance ratio. The Big Bang theory predicts it correctly. So we think we've got the time scales and the energy scales and the temperature scales. We think we've got that all right from 1 picosecond onwards. So that's how the universe came to be in 3 minutes. Nothing interesting happens for the next 377,000 years. The universe continues to expand. The universe continues to cool. All of the hydrogen, all of the helium doesn't do anything except get a little more spread out. We're not anywhere close to making stars yet. But after 377,000 years, something interesting happens. The universe is continuing to expand and continuing to cool, and when it reaches 377,000 years, eventually the universe has cooled to a temperature of 3,000 Kelvin. And that is a rather important number. It's the temperature at which, remember we're talking about, let's say for the sake of argument, it doesn't matter whether we're talking hydrogen or helium, the protons and neutrons, or the individual protons, are effectively what we now call the nuclei of atoms. They're positively charged, but eventually it's cold enough for these things to grab hold of the electrons that are floating around everywhere. I mentioned them earlier, didn't say much about them, but as well as producing protons and neutrons, there will be lots of negatively charged electrons all over the place. But until now, the universe was too hot. If you try and take a proton and get it to catch an electron, the universe was too hot. They would just rip themselves apart again. But now the universe is cool enough that we know it's possible for objects cooler than 3,000 Kelvin. We know from experience of laboratory experiments on Earth, if matter is cooler than 3,000 Kelvin, it is possible for atoms to form. It's possible for those positively charged nuclei to catch on to electrons. So for the first time since the Big Bang, 377,000 years have gone by before the first atoms are actually made. Up till now, the universe has just been a plasma of positive charges and negative charges milling around all over the place. But at this point in time, we can make atoms for the first time. So the universe changes from a plasma to a collection of atoms. And the crucial reason that's important is because the first time in 377,000 years, the universe becomes transparent. Up to this point, the universe was a plasma, and a plasma is a whole load of positive charge and negative charge, and light cannot travel through a plasma. It's effectively a whole load of, if you like, ionized atoms, a load of ions, a load of positive ions, a load of negative ions. The light that's trying to travel through this plasma will, like a pinball in a pinball machine, will keep ricocheting off all of these positive and negative ions and will never make any progress. But as soon as the universe turns transparent, then the light that exists in the universe, remember for every particle there are 1 billion photons of light rattling around, now it's transparent, that light can be released. And that light can indeed be seen. So the light that up till now was trapped inside the plasma because it was simply being scattered back and forth and back and forth, now we can see that light because it was released at that particular point in time. And we can see that light. When an object is 3,000 Kelvin, if you imagine, okay, it's not easy in everyday terms, but if you imagine heating up an object, after a few hundred degrees, it becomes red hot. If you heat it up more, it becomes orange hot. If you heat it up some more, it becomes white hot. An object that's at 3,000 Kelvin will be radiating white hot. It'll be emitting huge amounts of visible light and maybe a little bit of UV as well. So we are going to see that, but we don't see it as visible light because this light was released 377,000 years after the Big Bang, and since then, the universe has got an awful lot bigger. Because we're now at 13.8 billion years, the universe is now 1,000 times bigger than it was at this point. So the light has been released, the visible light has been released, and we see that visible light, but the visible light has been stretched 1,000-fold. Its wavelength is now 1,000 times longer than it was when the light was originally released. It was originally visible light, but now it's 1,000 times longer, and electromagnetic radiation that has a wavelength 1,000 times longer than visible light is what we call microwaves. And that's why we see the cosmic microwave background. The entire universe is bathed in microwaves because that is the afterglow of the Big Bang, released thousands of years after the Big Bang as visible light, now stretched out until we see it as microwaves. So when we look at the cosmic microwave background, this is a representation of the whole sky unwrapped into a flat plane so we can see it. So this is the entire sky. Some parts are just a little bit warmer than others. Roughly speaking, the same amount of light is coming from all directions because we're not in any particular special place in the universe. But there are small variations, a few parts in a million perhaps, a little bit hotter, a few parts in a million that are a little bit colder. Why is that? Well, because the original golf ball had dimples in it. The original golf ball had variations in density and variations in temperature, and those are effectively what we're looking at when we look at variations in the cosmic microwave background. Because different parts of the universe were slightly warmer or slightly cooler, and when the light was released, we get a slightly more intense or slightly less intense set of light or microwave photons coming in our direction. So studying the microwave background is what some people do because, in effect, it's a way of looking back to the very early universe. If we study the cosmic microwave background, the CMB, in detail, all of those small variations tell us about those variations in the early cosmic golf ball. We still deal with this as a hypothesis. We know the variations are there in the cosmic microwave background. We hypothesize that that's a result of the dimples in the golf ball. If the golf ball was perfectly smooth, we can't explain why we see those variations in the cosmic microwave background. So that's part of the whole infrastructure of the Big Bang theory. So various satellites, you may have heard of WMAP and Planck, etc., have been studying the cosmic microwave background to greater and greater precision because it gives us a window on this very early period before 1 million years after the Big Bang. So these dimples, I've said, ultimately will give rise to galaxies. It's difficult perhaps to see how, but we can run simulations which say, well, if we've got a golf ball with dimples, let's just take a simulation. Somebody has taken a big supercomputer and said, let's take a little chunk of the universe. I say little, it might be millions of light years or billions of light years on one side. Let's take a cube of the universe. Let's assume there are some little variations. Perhaps you can just about see there's a little bit of mottling. Some bits are a little bit lighter blue, some bits are a little bit darker blue. They represent slight changes in density of this region of the universe, and we're going to simply run the clock forward and let gravity do its stuff, and we'll see that over time different parts collapse and increase density, and after a little while we start to get the formation of dense regions of the universe which ultimately will form galaxies and galaxy clusters. Notice that the galaxies that are formed are not uniformly spread throughout the universe. They're clumped together in knots. There are these filaments or lines of galaxies. There are regions which appear to be almost empty of galaxies, these voids. So this so-called cosmic web is simply a result of start with enough hydrogen, give it a little bit of variation of density and temperature, let gravity do its stuff, you will end with a cosmic web of filaments and knots and voids, and that is precisely what we see when we look out into the observable universe. Remember that 3D atlas of galaxies? They're not uniformly spread. They're arranged in clumps and clusters and filaments and voids. If we were to look at what's going on in our immediate neighborhood, here's a sort of representation of, there's the Milky Way, and there are some of the galaxies around us. There's Andromeda over there, various small galaxies in our vicinity. That doesn't really tell us about the large-scale structure of the universe because our local group are gravitationally bound to each other. If we want to get an idea of what the universe looks like, we have to look at a bigger scale. So let's go out. So there's the local group right in the middle there. If we look on this larger scale, we see there are various clusters. There's a Virgo cluster up there. There's a Fornax cluster down there. Notice how these clusters or superclusters are arranged on what you might describe as a line or a filament. They're not scattered entirely uniformly over this particular volume centered on the Milky Way. They are quite definitely structured into what you might describe as a web. That's even more obvious if you go to a larger scale. We can see that we're in the middle there. The Virgo supercluster is right next door. And again, we see these lines of superclusters, and we see huge regions of space which appear to have nothing in them at all, or at least very little in the way of galaxy clusters, the so-called Boötes void, for instance. That's a direct consequence of the fact that the golf ball and the cosmic microwave background had a mottling, or dimples, if you like, and these dimples have collapsed into individual clusters or individual galaxies and given us this cosmic web structure, which is precisely what we see when we look out into the observable universe. Fast forward again, because time is precious. What happens in the next 13.8 billion years? Well, if we assume that after 3 minutes we've made all the hydrogen we need, and remember that, yes, there is some helium as well, but we don't need the helium. Stars are quite happy to process hydrogen and turn it into helium, and then turn it into carbon, and then turn it into nitrogen and oxygen and everything we need to live. Stars are quite good at doing that. But basically, the universe made all the hydrogen we need, shed loads of it, all made in 3 minutes. And if we have hydrogen, then we can essentially understand everything else. Okay, there are some details, but if we understand where the hydrogen comes from, now we can understand galaxies, and we can understand stars, and we can understand planets, and we know where trees come from, and we know where mountains come from, and snowflakes and rainbows, and we understand cats. Well, okay, probably not cats. Nobody understands cats, but if we start with enough hydrogen and give it a little bit of time to come together to form the cosmic web, to form the galaxies, the stars, the planets, etc., then everything else is a result of 3 minutes makes all the hydrogen you need, all of the raw material. Yes, I agree, there are some details of cosmic evolution to be worked out, and people are spending their life trying to understand how you go from shed loads of hydrogen to particular structures in galaxies or stars or anything else. But that is essentially the timeline. Let me just remind you graphically what we're talking about. Hypothetically, there was a golf ball. The observable universe was the size of a golf ball, I should say. Everything that we now see 100 billion light years across used to be just a few centimeters from each other. That was at a time scale of 10 to the minus 35 seconds. You can see the time scale is rather ridiculous because we go from fractions of a second up to millions of years and billions of years up to where we are now. So we start with a golf ball. We borrow energy from nothing, and we use it to make lots of quarks and antiquarks and electrons and anti-electrons and any other particle that takes our fancy, a so-called quark soup. After a few seconds, some of those quarks get together and make triplets, which we call protons, or a different triplet, which we call neutrons. So protons and neutrons are made in seconds. By the time we get to minutes, some of those protons have married up with neutrons in order to make the most stable structure that's possible at that time, which is the nucleus of a helium atom. So we're left with a certain amount of hydrogen and helium. Nothing happens for another 377,000 years until the nuclei that we've described here can get together with electrons. Nuclei positively charged, electrons negatively charged. We now have neutrally charged atoms, which means the light is released. The light is seen not as visible light, but as microwaves, and that's at a fraction of a million years. The big question which James Webb is now trying to answer, which is what happens next? After you've released that light, so you've now got radiation and helium and hydrogen, how do you make the first stars? And we don't know the details, which is precisely why the James Webb is looking back in time to these first few 100 million years, the first fraction of a billion years, trying to see the earliest star formation and the earliest galaxy formation, the so-called dark ages, because after the light is released as microwaves, stars are not born yet. So stars are not shining for perhaps a few 100 million years. We don't know precisely how many 100 million years until James Webb makes some more observations. But there will be dark ages before the first stars shine and then the first galaxies are made. And that is what we are currently looking back to. We can look back 12, 12 and a half, 13, perhaps 13 and a half billion years into the past to start to see what happened at the end of these dark ages when stars were being born. So we don't know everything. Although we've got a pretty good idea of the bare bones of the story, we haven't fleshed out all of the details. We know where the hydrogen came from. We know where the helium came from. We know how hydrogen and helium make stars and galaxies. But there are still some fundamental things which are causing us problems. The jigsaw is not yet complete. The remaining questions are, why? Why did matter win over antimatter? We can characterize the properties of matter and the properties of antimatter. We can make antimatter in the lab, that's not a problem. And we can see that they behave slightly differently. But the question is, why? Why does matter and antimatter behave differently? Why did the universe decide to make slightly more of one than the other? What caused the asymmetry in the first place? We're not denying that there is an asymmetry. We can measure the asymmetry, but why did it happen? We are eternally grateful that it did, otherwise we wouldn't be having this conversation. And of course, I've ignored dark matter. I've said, let's have a look at everything that's out there, everything that we can see, all the stars and all the galaxies. But we know, of course, that all of the stuff that's out there is not everything. We know that there is other stuff out there because, for instance, one of the bits of evidence for dark matter is that galaxies don't seem to rotate at the speed we would expect. The stars and the gas and the dust seems to be moving much faster than you can account for just from the matter that we can account for. So there's some other matter out there that's not being counted. And don't get me started on dark energy. Something is making the universe expand and accelerate its expansion. Everybody seemed to be quite happy with the idea that after the Big Bang, the universe expanded and continued to expand. And it was assumed that, of course, gravity will be pulling on everything, and so the expansion will be slowly slowing down. That was just taken as read. But then, a couple of decades ago, experiments were done and measurements were made, and lo and behold, the expansion of the universe is not slowing down. On the contrary, it seems to be accelerating. And dark energy is simply the label we give to the ignorance we have as to what's causing this acceleration of the expansion. It appears to be real. Some people would disagree with that. Some people would say we're doing our sums wrong. We're doing our calculations wrong. There's an error somewhere with the observations. But a lot of people seem to think something is making the universe expansion accelerate, and we don't know what that is. So the talk, of course, is entitled The Beginning of Everything, but I've tried to make it clear that everything in this context means everything we can see, everything we can measure, all of the stars, all of the dust, all of the gas, all of the galaxies, everything in between the galaxies. But all of that is only 4% of what's out there. Dark matter and dark energy account for the other 96%, which are still very much a mystery. But of course, that is entirely another story. Thank you for listening.